Everyone. In this video, we're going to be doing a deeper dive on bond graph modeling and really try to understand exactly everything that was going on in the last video when we did our bond graph modeling. So, we're looking at this mass spring damper problem where they're all in line, all in series, and you have a force that's happening on the left side of this diagram. Effectively, it's different from the other problem because these nodes right here are going to be moving at different velocities. They're not going to be the same. And that's because the force throughout the entire system is the same, but the flow or the velocity of the system is going to be very different for each of these components. And so we have a common junction of 0 right here because that's a common effort. The force is the same through the entire system. That's Newton's second law. For every reaction, there's an equal and opposite reaction. And therefore, this system follows Newton's law, and we're going to say that there's a force that's equal and opposite in every single component. So the force is the same. We have a 0 junction right here. We're going to have a source of effort coming in right here. This source of effort is going to have a value of F. And I'm going to talk about these lines right here in a later video. They're called causality, but I will go over that in a later video. So next, we're going to have an output here that's going to go into this spring right here, which is also a capacitor because it stores energy. Capacitors store energy, springs store energy, and it has a spring constant of K. Next, we're going to have a second output that's going to be a resistor, and it's going to be a damper, basically. The damper acts as a resistor. It resists motion. So that's what a damper is, and it has a dampening coefficient of B. And then we're going to have an inductor, or a mass, right? And a mass stores its energy somehow. And so we're going to have an inductor of mass M, right? So effectively at a 0 junction, all the forces are the same. But before I do that, I want to convert this force into a representation of momentum. So how do I do that? Well, what is force, right? Force, in a translational sense, is equal to mass times acceleration. Acceleration is effectively the derivative of velocity, right? So I'm going to write this notation as v dot. That's the derivative of velocity, right? And also, we can take that a step further by saying velocity is the derivative of displacement. So when we have the derivative of velocity, right, and we have displacement, I'm going to say that as x. And we're going to have a double dot. We're just going to add another dot to say that force is equal to the double derivative of x, right, which is displacement. What's momentum? I'm just going to arbitrarily choose this as momentum because later you'll see that this makes our lives super easy. Remember in the first video how I used x dot to represent velocity? There's a reason for that, and I'll show you later. But what is momentum? Momentum is equal to mass times velocity, right? And in our earlier example of force up here, we also stated that that could equal to mass times the first derivative of displacement, right? So we have this representation. Well, what is F equal to in terms of P, right? F is equal to x double dot times M, right? So that's also equal to, if I added another dot here, then I have to add another dot on the other side of the equation. So then I get P dot. I have to add a dot here too to make it true. But you get P dot right here is equal to F. So the derivative of momentum is equal to force. And so up here, I'm going to put P dot right here as the representation of force. And since that's common among all the junctions, I'm going to put a P dot right here. I'm going to put a P dot right here. And I'm going to put a P dot right here. Next, we're going to be going over each of these individual components, and I'm going to show you how I find flow from effort. Well, flow in the translational sense is velocity. Effort in the translational sense is force. So, let me clean this board right here. And let's take a look at this resistor right here. Let's take a look at this resistor right here. I'm going to be using red right here. Resistor. Well, what's the force on a resistor? F is equal to B, which is the dampening coefficient, times V. This is the equation for a damper. The force of a damper exists is the dampening coefficient times the velocity, right? So, effectively, I can also take that trick that I did earlier, and I can say F is equal to P dot, and V is equal to X dot. Remember the derivatives that we did earlier? And we have to solve for X dot, which is the flow. So what is X dot? Well, X dot is P dot over B, right? So that is our flow, P dot over B right here. So I'm going to effectively put a P dot over B right here, right? Next, what I'm going to do is I'm going to say that capacitor right there. I'm going to ask, what is the flow of that capacitor? Well, we're going to do the same thing that we did for the resistor, and we're going to say, what is the force that a spring exerts? Right? What is the force that a spring exerts? Well, F is equal to K, which is the spring constant, times X. Right? Not X dot, just F is equal to K times X. F is equal to P dot, which is equal to K times X, but we're not looking for X right here, but we're going to solve for X right now, because that's the easiest thing we could do. X is equal to P dot over K, if I bring K over to the other side. Well, we're looking for X dot, so we're going to add a dot on this side. Then we're going to add another dot on this side because we added a dot on the left side. And we're going to get P double dot K. So P double dot over K is the flow of the capacitor right here. Next, we're going to look at the mass, and we're going to do the exact same thing. Let me erase everything. Okay? So we're going to look at that inductor, or the mass, right? Well, the inductor is basically a mass, and what do we know about the force that a mass applies? Well, F is equal to ma. And we already did this equation before because we defined this by saying F is equal to P dot and M is equal to X double dot, right? The double derivative of displacement is acceleration. So we're going to solve for X double dot because that's all we have, but we need X dot. So we're just going to say X double dot is equal to P over M, P dot over M. We're going to take out a dot here, so we have to take out a dot on the other side, which leaves us with the equation X dot is equal to P over M, right? So the flow of a mass is equal to the momentum divided by the mass, which actually makes sense because momentum is equal to mv. We divide mass from that, we get velocity, and velocity is flow. But we're going to use this equation instead, P over M. We might be interested in this junction right here. We might be interested in what is the velocity of this junction right here when we apply a force to it. So I'm going to designate this empty space for flow as V. To get the answer to how to find an equation for this bond graph, we need to understand the conservation of energy, right? And more importantly, the conservation of power. What do I mean? Well, I'm going to write down energy right here. Power is equal to energy over time, right? And time is just one of those variables that changes the same for all the components. So it's proportional to energy right here. And energy has to be conserved. But what is power? Well, power is flow times effort. And another definition would be power is force times velocity, right? And we have a force right here, and we have a velocity right here. So effectively, by summing everything up together and multiplying the force and the velocities together, they should all equal 0 for this junction right here. And as you see, they will be. So let's multiply the forces and the velocities together to get power. In the first junction, it's positive since the value is going in. Sorry, I'm putting causality. I'll go over that in a later video. It's just bothering me. Next, we're going to have P times V. And it's positive because it's going in. Second, we have the resistor right here. And the resistor, we're going to have a negative because it's going out of the junction. And we're going to have a P dot times a P dot over B. Next, we're going to have the capacitor, or the spring, and we're going to multiply that together. And we're going to say P dot times P double dot over K. The last component, the inductor, we're going to have minus, again, because it's going out of the system, a P dot times a P over an M is equal to 0. Then we can divide out the P dots, and we'll get V minus P dot over B minus P double dot over K minus P over M. And I'm going to put this in parentheses just to reiterate the point that I can factor out the P dot. I have a 0 on the other side, so when I divide out by P dot on both sides, P dot divided by P dot is 1. Therefore, we just get V minus P dot over B minus P double dot over K minus P over M is equal to 0. This is a representation of the dynamic system, and when I want to solve for the velocity at this junction right here, that's highlighted in blue, I subtract everything out over the other side, and I get V is equal to P double dot over K plus P dot over B plus P over M. And this is a second-order linear differential equation that can be solved for P double dot, which is impulse, P dot, which is force, and P, which is momentum. This is a very powerful thing because once you solve those, you have a way of representing this system over time to see how the mass would move, to see how the spring will move over time, to see how that force will move over time, to see what the force is at a certain point. You can have these different graphs, and you can represent this dynamic system. You can effectively change K, you can change M, and you can change R and see how that system reacts to that input or output that we have. So that is effectively the deep dive explanation of how I create a bond graph with a single junction. Thank you for listening, and I hope to see you later.